Much of today's high-tech equipment requires specialty wires and cables. From stage lighting to medical devices to robotics, wires and cables have to be custom designed and expertly manufactured to perform in a specific way and withstand various environmental conditions. Cables can be designed to withstand high temperatures or perform special functions such as sensing pH levels or proximity to objects. At the heart of a cable are electrical wires, called conductors. A conductor begins as a bare copper wire. This extrusion machine coats it in plastic. Chilled water solidifies the plastic around the wire as insulation. This isolates each wire from its neighbors. Every conductor passes through a machine called a spark tester. It runs current through the conductor to ensure the insulation is flawless. If there's even the smallest break in the insulation, the machine will sound the alarm and locate the spot. The conductor then enters a machine called a cabler. It unrolls spools of insulated conductors and unites them with other components to form the cable's inner workings. At the center of this particular cable is a twisted pair of insulated conductors. Around them go color-coded insulated conductors and fillers to fill in the gaps between the conductors, giving the cable a smooth cylindrical shape. Here, the fillers are strands of polypropylene foam. An orientation plate aligns the components in the proper configuration as they enter the cable assembly die. The components exit the die with the fillers wound around the insulated conductors, which wrap around the central wire. The next machine, called a taping head, wraps binder tape around the cable. This tape holds everything tightly in position so that the assembled components don't unravel. This is a different type of cable assembly machine. Like before, all the insulated conductors unroll from their reels and travel through the holes of an orientation plate. Dies divide the 6 conductors of this cable into 3 groups of 2, twisting the conductors of each pair together. The machine then wraps each twisted pair in a shield made of aluminum-coated polyester. Shielding eliminates what's known as crosstalk, signals interfering with each other. The next die joins additional wires that don't need to be shielded to the shielded ones. Then everything gets twisted into one cable. Then a final twisting, seen here in slow motion. The actual speed is 1,000 revolutions per minute. The next machine wraps tissue paper around the cable. Then an extruder applies a jacket made of a plastic and rubber compound. The tissue paper acts as a separator, preventing the jacket from sticking to the cable inside. Sometimes, instead of tissue paper, the cable runs through a bath of talc. Talc is a mineral that absorbs heat, so, just like tissue paper, it prevents the jacket from sticking. Once again, as the cable exits the extruder, chilled water solidifies the molten material into a jacket. A wheel with raised lettering imprints the manufacturer's name and technical specifications into the jacket. Certain jacketed cables need a braided shield to eliminate electrical interference. This machine has 48 carrier spools, each of which holds 10 wires made of tin-plated copper. As the jacketed cable moves upward through the machine, the spools move in a programmed pattern, weaving the shield around the cable. From there, a last trip through the extruder for a final thermoplastic jacket. And the custom-made cable is ready to be connected and powered up.